Welcome everybody. My name is Mike Huls. Today I'd like to talk a bit about how Python isn't as slow as you might think. And for this we'll take a look under the hood, examine the way Python is designed. And lastly we take this new knowledge and combine it with a few examples so we see how to improve Python's performance. So we'll start with a quote. Why do you use Python? Isn't it really slow? I don't know about you, but I've heard this more than once. And it kind of annoys me every time because it's kind of true. Python is a bit slower than other languages, but not as slow as they think. So what I'm here today to argue is Python isn't necessarily that slow. It's actually pretty fast, although not as fast as languages like C or Java, for example. And the second thing is Python is a tool that's designed for a specific job. I wouldn't write an OS in Python. I wouldn't write a web page in C, and I wouldn't write a game engine in JavaScript. Especially, it's not that it's impossible, you can very easily do it, but there are better tools. Especially when you take productivity into account, suddenly it's okay if your web page is a bit slower, like a few milliseconds, if it saves you a few hours or days of programming. So the goal of this talk, first, we'll take a look at how Python works to have a deeper understanding of it, so we can apply it better in the right place, in the right way, so you become a better developer because you write better code. First, a little bit about myself. My name is Mike. I'm 33 years old, and I live in Groningen with my girlfriend and my 2 boys. I'm the one at the left. For the past 2.5 years, I work at Data Next here in Groningen. We build a customer data platform. We primarily support business-to-business clients in visualizing their customer data, making their customer data actionable, and also automate their marketing. I'm part of the data development team where we combine data engineering with a good bit of development, so we have a very broad toolkit, of which Python, of course, is the main one. This is our building. We just moved here. And we also are looking for people, so if you want to know more, just talk to me. I used to have other hobbies like bouldering and traveling, but then our twins were born 2 years ago, so you know how it goes. I'm a self-taught programmer, and when I first started using Python some 10 years ago, I was just getting it to do what I want, which was pretty easy because Python is pretty beginner-friendly. But then as I got a little bit more experience with both Python and other languages, I started wondering, seeing some differences and wondering things like, why don't I have to define variable types? What's an interpreter? Why does everybody hate on the guild that much? How does Python collect garbage? And eventually, why is Python slower? And I believe that these questions can be answered if you know more about Python's design. So this is what we're going to do today. 2 parts. First, we'll check out how Python is designed. And then we check out how we can, this is kind of the theory part. And then comes the practice part. We take the knowledge and apply it to circumvent slow code. 2 small disclaimers. Especially in part A, I'll use a few examples that are a bit simplified for clarity. And the second one, when I talk about performance, I'm talking about slowness, not waiting. If you have to wait, for example, for an API response or a file to download, that's not Python's fault. You can rewrite your whole program in C, but C cannot wait faster. This is a difference between I/O and CPU, which we'll get into a bit more later as well. So let's start with a beautiful definition. Don't read it, a lot of big words. We'll quickly chop it up into little bits and go through in these 4 chapters. So let's start with dynamically typed. As you might all know, Python is a very high-level language, which means that it's designed for humans to read and understand. It also means that it takes away a lot of low-level complexities like computer hardware and system operations that are abstracted away from the developer. And an important part of this is the fact that Python is dynamically typed. This means that we can do something like this. We can just specify a variable name, assign a value. This is different in other languages, like in this case, for example, Java, where we also have to define the data type. Also in dynamically typed languages, we can do stuff like this. We can take the same variable and assign a different value of a different data type. This would not compile in Java because the data type is already specified on that variable. So there are a few pluses and minuses, and it all comes down to ease of use versus how easy it is, or how performant your code is. Because if your definitions are more rigid, you're less flexible, but your code performs a bit better. Please also note that Python does have variable types. It's not untyped. You just don't have to define it. Python has to know your variable type at some point. And this is where the interpreter comes into play. In order to understand the interpreter a bit better, we first need to talk about compilation. This is some source code I've written in C. It's a very simple program that just prints hello world. Source code is like the code that you write. Machines cannot understand that. So they first need to translate it into something that the CPU can read. This process is called compilation. And in C it's pretty straightforward. You supply it with some source code. It compiles the whole thing and then it runs it. In Python this works a bit different. Imagine we have a function, which is our source code. Python runs through an interpreter, which means that it doesn't compile your whole file all at once, but it goes through your file line by line. And when it arrives at, for example, the return line, the Python compiler, which is part of the interpreter, first compiles this piece of code into bytecode, which takes the return value **3 and splits it up into 4 separate bytecode instructions, which are then interpreted by the Python virtual machine into machine code that your machine can actually execute. So obviously there are a lot of extra steps compared to C, but there are also a few plus sides. For example, your code is a bit more platform independent, since the interpreter handles all hardware and OS specific optimizations. For example, if you compile C, you need a specific compiler for your system. In Python, you just install it and it runs. This interpreter also plays a large part in Python's interactivity. You can just start your code and run it without the need to compile the whole thing. So this not only saves a bit of time when you have large code bases, you can prototype a bit more easily. You can cache the compiled bytecode, by the way. And the negative part, of course, is a bit of overhead because it has to do some extra work. So, now that we know how the interpreter works, let's see how it actually remembers these variables, for example, value. This is the way Python stores variables in memory. Let's first look at how C does this. We take an integer called the answer, apply the value 42, of course. What happens here is that C checks out the answer. It knows that it's an integer. It knows that it requires 2 bytes of memory, for example. It looks for a place in memory where there are 2 bytes available, and it saves that address. Inserts the value 42 into that location and points the answer to that location. So this is pretty straightforward. C owns a part of memory. So the answer owns a part of memory directly. Also, in C, we can do things like this. Because we know that the answer is an integer which requires 2 bytes, we can overwrite it in memory. So we can store a new value there, like this. The location doesn't change. In Python, this is a bit different. Imagine we have the same thing again, a variable called the answer, value 42. When the interpreter gets to this line, the first thing it does, it creates a Py object. And the Py object is what people say when everything in Python is an object. It is a C struct that lives in Python's memory, and it contains all the valuable or the relevant information about the variable. Also, a Py object is always of a fixed size. It's always, let me see, in a 32-bit system it's 16 bytes, 64-bit system it's 24 bytes, always. So that's how it can allocate this memory. So, first thing that the interpreter does is create a Py object and store some interesting information about this variable, namely its type and its value. Then it creates a Python name, that's called the answer, and it points to this Py object, incrementing its reference count by 1. So, this is quite some extra work. Let's see what happens when we do this. We try to override the answer. First thing the interpreter does is it creates a new Py object at a different place in memory. Then it destroys the link between the Py object and the Python name and decrements the reference count because it's referenced by 1 variable less. It points to the Py object, the new Py object, increases the reference count, and that means that the old Py object there are 0 variable names that refer to it, so it can be garbage cleaned. This is also the reason why we can do things like this in Python. We can override the answer with a completely different data type. Again, a new Py object gets created. It's of a different type. It has a different value. We just point it again, up, reference count, clean up the old object. This is a bit of quite different from C, and it has a few downsides and upsides, but mostly downsides. Python has to do a lot more to create these Py objects and Python names. It has to increment, decrement the reference count. It has to find all these objects in memory. It has to point the answer to the correct memory space again. Second one is it's more memory inefficient because the Py object is 24 bytes always on a 64-bit system. Imagine you store an integer, you're going to need 24 bytes. Imagine you store a string, you're going to need a lot, even more bytes maybe. In C, this only requires 2. Additionally, we need a lot more objects are created because we cannot overwrite. For example, if you're in a loop, for every entry in the loop, it has to create a new variable or a new thing in memory. Number 4, more objects mean more garbage collection. If you have to do more work garbage collecting everything, that means your code freezes for a moment while it's being garbage cleaned. Quite different. The next part is about the GIL. We just saw how Python remembers and forgets variables. This is the next important part, and it also plays a little bit with the previous one. So, what does the GIL do? Shortly said, it ensures thread safe memory access. This doesn't mean that your program is thread safe. Your program can be very thread unsafe, but the GIL at least ensures safe memory access. It does this by allowing the interpreter to only execute a single line of bytecode at any given point in time. What I mean by this is this. For example, you have 2 threads. They both have the answer variable as well. They both point to the same Py object. What now if both of these things get deleted simultaneously and the GIL doesn't exist? So they both read the reference count. They both read a 2, subtract 1, and write it back. Then both of these variables get deleted, and this Py object remains in memory for as long as the program runs. This is not what we want, because then your memory gets fuller and fuller. This is where an object incorrectly doesn't get cleaned. Even worse is when an object incorrectly gets cleaned. This is not what you want at all. So this is what the GIL does. It prevents that such situations like these can happen. It also eliminates the need for thread sync mechanisms, which are complex and error-prone. And it has an exception for I/O-bound tasks. CPU-bound tasks are limited by the GIL. I/O-bound tasks, they may pass, so you can wait, for example, for multiple API responses at the same time. Last thing, if you multi-process your code, every process has its own Python instance, its own interpreter, its own GIL. So every process has the same restrictions. So, a lot of theory. What we've seen is that we can, with Python, we can easily write, run, read, understand, and maintain our code. It's pretty easy to do that, but we pay a little price in performance. This is what I call the productivity versus performance thing. Because Python has to work a bit harder to take some work away from us developers. And now that we're a bit more familiar with how Python operates, we can apply this knowledge and check out how we can improve its performance a bit more. The most important step in this one, before we check out the examples, is to know the source of the problem. To really think about what your problem is. So, for example, if you have a lot of I/O, you can solve this by running threads. If you have a lot of CPU, use multiple processes. Are you doing a lot of looping? As we'll see in one of the examples, you can check out built-ins or restructure your code so that your program doesn't have to work this much. We'll get into an example of this. And if this is still not enough, you might extend your Python code with, for example, another language, which we'll get into as well. So, let's get into the examples. This is a simple example. We need to write a function where we receive 2 lists, and we return how many items in both lists appear in both lists. So, for example, if we get the left list and the right one, it will return the number 2 because the 1 and the 5 are present in both lists. It's pretty simple. We have 2 lists, both 5k words, 5 letters long. And the most straightforward and most dumb way to do this is this. And people who took note, they might see the problem already. We have 2 lists 5,000 long. So if you check out this part, for every item in list 1, for every item in list 2, that means we do 5,000 times 5,000 operations. And for every one of these, we need to stringify item 1 and uppercase it, and do the same thing with item 2. Stringifying and uppercase it mean that new variables have to be created in Python. This means that a new Py object has to be created. Their new memory has to be found. A lot of work for your interpreter. So you might not be surprised that these are over 25 million function calls at least, maybe even far more. And it takes around 16 seconds. So the only thing I did here in this next example, I've moved the stringify and the upper from the lower box to the upper one. And this saves quite a lot of performance, because here you have to only do the stringify and the uppercase 5,000 plus 5,000 times. And then we can compare the items and add them to the duplicate set. This is not 16 seconds, but it's only half a second for a little small performance increase, which we now know is possible because the way Python handles its memory. An even better example is to use built-ins for this. We can easily convert the both lists to sets and then use the intersection, but okay, that's the next part, so let's get into the built-ins now. Again, we have a function that deduplicates a list. Really easy. The problem is in the entry not in return list. We can rewrite it into this. We still do the stringify in the upper method for every item in the list, but then we add it to a set. And a set is a built-in data structure, so it's, as you know, Python's written in C, it's implemented in C. It's much more memory efficient, which means that we cannot do this in 57,000 milliseconds, but only in 22. So this is extremely fast. It's only 2,600 times faster because we take away a lot of work from the Python interpreter and let it handle it in C. The next example has to do with Python, or with Pandas. We first create a data frame. It contains 1 million rows. We just do this code. This is what it looks like, only it goes till 10 million instead of 5. Our goal is to square all the entries in column A. So we want to end up with something like this. First contender is pandas.apply. We can just, for every item in the list, apply a lambda function which squares the result. This takes around 7 seconds. The second contender is to use pandas vectorized. And this takes only 28 milliseconds. Now, why is this so much faster? Again, because we use the built-in pandas function. In the left example, we do both the arithmetic operator, so the squaring in Python, as well as looping. We do it in Python. It is a pandas function, so you might think like, hey, pandas is really fast. Why is this so slow? The looping actually happens in Python instead of pandas. And that's what we fix in the vectorized version. Looping here happens in Python. In pandas, I mean. Even faster is the np.square function, which not only allows you to run the loop built into the NumPy, but also the squaring operation. So this is even faster. Last part is about extending Python. Extending Python, I mean like rewriting parts of your code with another language like C, Rust, or with Cython. And this might seem a little cheaty, like how can you speed up Python? Yeah, just rewrite it into some other code. But this is not what I mean. What I mean is you have to write your entire program in Python, which is really fast, you're really productive. Then single out the bottleneck and only rewrite that single code, that's a single function in a language that's a bit more difficult to learn. For example, if you have a very large application with a single program, a single function that's pretty slow, you can rewrite the single function. You don't have to be a Rust expert. For example, if you have an API and a single function is slow, I don't have to write my entire API in Rust, for example. I have some blog as well where I show some examples about extending Python with C and Rust and Cython. For now, we'll just focus on the Cython part. If you want to read more about this Rust and C, just check out the links below. And now we'll talk about the Cython thing. So we have some very unoptimized function for finding primes. This finds prime numbers between 0 and a certain limit. It's not designed for, there are more efficient ways to do this. I just need a function that needs to calculate a lot so I can demonstrate more clearly. Let's benchmark this between 0 and 50k. So we find out how many prime numbers are in between here. And if we do this in Python, it takes around half a minute. So first thing we do is we copy our code into a pyx file. This is the Cython file, compile it, run it, and it's already 2 times faster just because it's compiled. Next, in Cython, we can add types, and this looks like this. So here we say, okay, count is an integer. We define the count as an integer, so we can pass Cython a bit more information about our program, which allows Cython to convert this code into C code, which runs more efficiently. And when we pass types, we optimize like 25 times compared to pure Python. Additionally, last thing, we can add compiler directives, which says to Python, hey, don't bother checking for null divisions or divisions by 0, none checks, and the wraparound and bound check they have checks for slicing lists. And if we do this, we even are sub-second with the same function in Python. So if you have a large application where this is the problem function, I only need to optimize this little tiny function. I don't have to be an expert at C. I just have to know enough about it to get this to work. And we can even multi-process this whole thing now. Some last alternatives. I'm not really. These are not the only ways to improve performance in Python. There are also things like Numba, Ray, Dask, and PyPy. I'm not really experienced with these things, but just know that they exist. Numba compiles pieces of Python code to machine code just before executing it. PyPy is an alternative Python implementation that focuses on performance improvement through a JIT compiler. And Dask and Ray, they allow you to spread out all your computation not only over multiple processes, but also over multiple machines in a cluster. So this can improve performance as well. Again, not really experienced, just know that they exist. So, in conclusion, Python is a great tool. It's very easy to use. It's so easy to use that it's very easy to hold it incorrectly. But now that we understand more clearly about how Python works, I hope that we can really understand your tool a bit better, so you can hold it correctly and you can apply it at the right place and in the right way. A few links if you want to connect or maybe become colleagues. And I want to thank you for your attention.
Thank you, Mike. We have some time for some questions. Anyone? Questions for the audience? Are you, Guy? Yeah. So the question is, Python is dynamically, it's dynamically typed, not typing. So I can't. Maybe you can repeat the question.
I think maybe you mean that do type hints improve performance? Yeah, that's indeed. At the moment, I think not. I am fairly sure that they don't improve performance. Actually, they're just for the developer to provide more information about your code. I think when your code is compiled, like these are just like comments, they just get ignored. Oh yeah, I really like that. It actually slows it down a little. So don't type in. But is it like a slowdown of a lot or a nanosecond here and there?
Well, you have the modules. If you have the modules, they can be very tricks in typing to do that. So like if you run introduction, you don't use no typing in development, then it slows down.
Okay, there's a little slowdown using type hints, but there are tricks to to not have them in production, but have them only in development. Interesting.
Yeah, so you spent a lot of words about like explaining why Python is slow, and you showed some like contrived examples. But I was wondering like what your thoughts are on how to approach finding the slow part.
My approach. Oh yeah. What is my approach on finding the slow part in Python? Well, most obviously during development you just notice. I think. Sometimes you can like guess at it a bit, but I usually also use the C profiler, for example, to check out what my code does, how it runs, how many function calls it does. For example, the example with where we loop through list 1, and then for every item loop through list 2, you can see in the C profiler that it has like 50 million function calls, which take up a large amount of time. That's my most used way to find your biggest slowdown.
My question is it really on Python use C language for handling exceptions, for example? Is it really or not? Will it give a more speed up?
Using exceptions in Python?
No. Using rewrite Python code and emulate exceptions on C.
Exceptions in C.
On C language, I mean.
If the exceptions are handled in C in Python?
I have a Python code.
Yeah.
I would like to put it to use C language for this piece.
Yeah.
Is it really to emulate exceptions in this C code?
Oh.
And will it give speed up or not?
Oh. Do you mean if you have a piece of Python code and you optimize one little piece, how does that C code handle exceptions?
Yes.
Not really sure, but I think there might be things in place that bubble up the exception to Python.
Okay.
That's it.
Okay, thank you very much. Give him an applause.